I don't know. This is the end of my notes list. What's that? Time is over. It's almost fine. You literally just crying. It's pretty good class. Oh, but it's not. It's Inference. So what do you think?
哦，对，好好的，挺好。
What is the topic of the topics and questions?
Social.
You looking at it? Are you ready?
现在正在卖 PB16。
Okay. Good afternoon, everyone. Let's start. So in the last lecture, we have wrapped up the Barkley model inverse, namely the Theta algorithm, right? So how to efficiently calculate the marginal distribution of one variable or a set of variables in your graphing models. We then talk about everything on factor graphs. So at the end of last lecture, we have introduced a simple extension of sum product algorithm. We call it maxsum. So maxsum algorithm is used to find out the maximum joint probability. This is actually very important, especially in method structure prediction tests, like in NLP. You want to keep the you want to assign a part of speech text on the words in your sentences, right? So of course, those neighboring words, they form a kind of a Barkley model. Typically, they will change like chain structure Barkley model. So I want to find out an optimal setting, an optimal configuration of those POS part of speech tagging, and to make it reasonable, right? So to do that, we need to find out the maximum joint probability as well as the setting of those random variables that achieve the maximum joint probability, right? So how can we do that? So actually, just make a simple modification of the sum product algorithm. So if you want to find out the maximum joint probability, we can do we can first take logarithm of the joint probability, right? And then we will maximize this log joint probability. And because the joint probability is factorized as a product of the factors, right? So according to the definition of the factor graph, it will be a product of the factors. So your log joint probability now becomes the summation of log factors. And then you maximize this. You maximize this summation of log factors. Right? So we then find that when we do this max and sum, we combine the max operations and sum operations, right? When we do this, it's still a based distributive log, right? So generally, if I want to calculate the max of a plus b and a plus c, it is equivalent to first doing max on b and c, and then do the summation on a, right? So it obeys exactly the same rule, same law as we couple the sum of product operations, right? The sum of product operations, they obey the distributive law as well, right? That being said, we can simply redefine the sum and product operations. How can we do that? So if this is our original sum product algorithm, right? So if now we redefine the sum operation to carry out the max operation, and redefine the product operations to carry out the sum operation, then we can efficiently conduct this max sum calculations, right? So we follow the same idea, like we want to switch the sum and max operations. We want to do as many max operations as possible before we do the sum operations. In doing that, we can save a lot of computational costs, right? So same idea. So we simply just simply replace the original sum operation by max and replace the original product operation by sum. Then we'll implement our algorithm to find out the maximum joint probability. So at the end of last lecture, we also mentioned that how can we also augment those messages such that we can backtrack all the settings or all the configurations of random variables to achieve the maximum joint probability. Right? So it's a very simple extension, but I still saw a few pieces are confusing. Maybe we're taking too fast. So today I want to spend more minutes to give you a concrete example to see why by adding some add max operation we can backtrack all the setting of the random variables and to ensure that those setting of random variables will arrive at the maximum joint probability. And hopefully, after I give this explanation, we'll be very clear about this algorithmic details. Okay, so let us start with max sum. Right? So as we said, we simply replace max sum by max. Sorry. We simply replace sum operation by max and product operation by sum. We end up with a max sum algorithm. So in more detail, again, like in the original message passing algorithm, we need to look at the initial messages, right? So the initial message passing meaning that okay, when two cases, first when we have a one variable x, it only connects to one factor fa, right? So what's this message from x to the factor fa? So in our original sum product algorithm, simply 1, right? But now, remember, we're doing the logarithm over all the factors, so it will be 0. And in another case is that if fa is a leaf, and the factor fa is a leaf, and I just denoted by f. So if a factor f is a leaf, and it only connects to one variable, right, how can we compute message from this factor f to its neighboring variable x? So in our original sum product algorithm, it will be the factor itself, right? It will be simply the factor itself. But now, because we take a logarithm of the factors, so our message will be logarithm of the factor. And then let us look at the definition of the rule to compute the two types of message. Two types of messages. One type is to pass message from a factor to a variable. The other type of message is to pass a variable to a factor, right? So you'll find the correspondence to the original sum product definition. So first, if we want to compute a message from a factor node to a variable node, and in general we assume, okay, this factor also connects to big M other random variables. So we denote those remaining neighboring variables by x1 to x big M, right? So then in the max sum algorithmic framework, when we compute message from f to x, we're going to first take logarithm of the factor. This is consistent with our definition here, right? And then we plus. Remember, we replace the product now by sum. So now we're not multiplying with other messages. We're adding other messages. So add messages from the neighbors of f means x1 to xm to f. Right? So remember, each message is actually a function of a variable. So the message from the variable x1 to f is actually a function, see, g x1, right? So message from x2 to f is a function of like x2. So you can imagine like this is a function. The logarithm factor is a function of x and all its neighboring variables x1 to xm, right? So those are a bunch of summation of functions. So if you add them together, you end up with abstractively a function of x, x1 to x big M. Right? Everyone is comfortable, right? So now we do the maximization over this summation. Remember we just replaced the max, replaced the sum in our original sum product by max, right? Now we do the max operation over the neighboring variables x1 to xm of f. Right? So here I want you to be aware that this will still end up with a function. So for each particular value of x, I'm going to max this summation over x1 to x big M. So that means, okay, if x taken to be 0, right? And I have a setting of x1 to xm that maximize the sum, you end up with some message value to be 0.3, which is maximum. Right? So if I take the value of x to be another value, say x equals to 2, x equals to 1, right? So you might have another setting of x1 to xm to arrive at maximum. And the message will be, say, 0.4, and go on. So although we take maximum operation, remember, we only take part of the variables. So still end up with a function. So keep this in mind, because later we'll explain how we use this to backtrack all the optimal setting of x1, xm to ensure each message value is maximum. Right? So this is a way to compute the message from a factor to a variable. So now let us look at how we compute the message from a variable node to a factor node. Right? So in general, you're going to assume that x node only connects to f, but also connects to another set of factors. Right? So we can denote, we can draw the other set of factors. So in the original sum product rule, you're going to just multiply the messages from all the other factors to x. Right? But here, remember, we replace the sum by, replace the product by sum. So here, we calculate message by simply adds up the messages from all the remaining factors connecting to x. That's it. Right? Is everybody comfortable? So everyone agree with this point, right? It's just a simple modification of your original sum product algorithm. You just replace sum by max, replace the product by sum, right? Previously inside this parenthesis, no square bracket, we're doing multiplication, right? But now we replace this by summation, because we do the logarithm with that. And previously, when we capture the message from a variable node to a factor node, we're going to multiply all the messages from the other neighboring factors, right? But right now, we do the summation. But now the question is, no. And then we just follow this protocol. And then we carry out the same 3 steps. The first, pick up the root to construct the tree, right? And second, we collect, starting from leaves, we do the message passing and collect messages to the root. And the third step, I distribute message from the root to all the leaves. Exactly the same procedure. You compute all the messages. So after we have calculated all the messages, how can we calculate the final, maximum drop probability? Anyone recall? It's very similar to compute the marginal distribution, right? So you can pick up any node in your fractal graph, right? So and look at all the factors connecting to this node, right? So we just sum the messages from all the neighboring factors to this factor, right? So let me simply denote the. So suppose this is a node X, right? So let me denote its neighboring factors by F1, F2, and F3, right? So I just as a all the factors, the messages from all the neighboring factors to X. So this mu I into X. Remember, this is still a function of X, right? So now what I do, what should I do in the next step? I want to compute maximum drop probability, right? So now given all the messages already, I just collect all the incoming messages to X, right? Add them together. Now how can I get the maximum drop probability? In a sum product algorithm, we just multiply them together, and then we do the normalization or calculate marginal distribution. In the max sum algorithm, we do the max, right? Again, we replace the product by sum, right? And we replace the sum by max, right? So we do the maximum. Then we'll end up with the maximum drop probability. Does it make sense? Right? Just replace the operation. Right? More abstractly, you can define the so-called sum and product by whatever calculations you want, as long as they follow the distributive laws. So this is the more abstractive level. Like when I was a grad student like 10 years ago, I implemented this whole bunch of message passing algorithms in general graphs, arbitrary graphs, and I didn't write a separate algorithmic procedure for sum product max sum. So guess what? I used the C++ operator. How should I say that term? I even forgot. I was an expert in C++ 10 years ago. You can define operator, right? You can define what is sum. You can define what is product, right? You can define operator on that. But you can implement different implementation in different function over the same operator, right?
Operator overload.
Yeah, operator overload. Yes, exactly. I just define a fancy template. It's called meta program, right? Template programming. I implement everything. Every time I just instantiate with different operator. That's it. I never need to implement this same algorithm twice. So now if I pass out all these incoming messages, I do the max operation, I can end up with the best or the maximum drop probability. Then another important issue is that how can I find out the value of each random variables in your graph that arrive this maximum drop probability, right? So from this particular node, I can find out the corresponding optimal configuration. Why? Because I just look at which x have this maximum summation, right? But how can I trace back to the optimal setting of the neighboring and the neighboring random variables? That's an issue. So in many cases, actually tracing back the optimal configurations of all the random variables are even more important. Why? Because I want to know the setting of those random variables. I do not want to know what is the exact value of this max joint probability, right? So when you do the post-tag part of speech tagging or whatever parsing steps, right? I want to know which word is labeled as, say, named entity or whatever, a verb or a noun, a preposition, such kind of stuff. I do not care whether your joint probability is 0.0001 or whatever, right? So in practice, it's more important to find out the optimal setting for that, right? How can we do that? We mentioned in the last lecture. By doing this, we can simply, when we do the message parsing, we will not only record the maximum value, right? We also need to record the argmax. So that means your message will consist of two components. So let us denote the other component by like mu hat, right? So mu represents the message value, the maximum value of this summation. But mu hat store the setting of the variables which achieve this maximum. So usually, I mean, for succinct notation, we just represent as argmax. And the same thing, the same expression here. So that means, okay, every time when I calculate this message, I'm not only calculate the maximum value, those summation, I also record the argmax, meaning which set of x1 to xm will ensure that this summation achieves the maximum for a given max. Right? If we take a look at the message from a variable node to a factor node. Right? So here we do not do explicit maximum computation, right? And how can we do the argmax? Any idea? So actually, I mentioned in the last lecture. So remember, each particular message in a summation is a factor message. It's a message from factor to a variable node, right? So they have a long with argmax, right? So here we will compute the message from variable node to factor node. You just merge all the argmax of the messages you're adding to. Then you record all you record the associated setting of the random variables. So let me give you a concrete example. So that would be better. So suppose I have a factor of x, right? So when I calculate the message from f to x, suppose f also connects two other random variables, x1 and x2, right? So when we calculate this message, I mean the maximum value, for each particular x, I'm going to have a value, 0.1 or 2, 3, right? But when we do the argmax, I'm going to record the setting of the corresponding x1 and x2. So that being said, this argmax message essentially a table. So you have x, you have x1 and x2, right? So for each value, each possible value of x, say x taken to 1, well, you have a setting of x1 to x big M to maximize this summation. So here we have only two variables. So the two variables might be like 1 and 2 to ensure your summation is maximum, right? But now if you change x to be 2, you have another setting of x1 to achieve this maximum summation. So that might be just blindly write down. So it could be 0, 1, and blah blah, and onto k, it might be 3 and k minus 1. So see, the second message, when we compute argmax, essentially we call a table. And this table links your variable x and the associated variables x1 and x2, which connects to have all the maps, right? So you can imagine if every time I recall such kind of table, so from, as we just mentioned, at last step, I pick up arbitrary node, right? I find out maximum value of the summation of the incoming message. I end up with the maximum joint probability. At the same time, I can pick up the optimal value of this particular x. Right? And then from this x, I look up the table. I can find out the optimal setting of the associated random variables. Right? And with this optimal setting of associated random variables, I look up another set of tables. They are computed from all the messages. And do it again and again until you cover all the random variables. That's how we do the trace back. So this is the key idea. So we can take a look at when we compute the message from variable node to a vector node. Right? So as I just mentioned, if I want to also preserve the argmax, right? So actually we do the union of the argmax message of all the neighboring factors to x. So suppose this is x, right? So this is x. This is x. When I compute the message from this x to the factor f, right? So suppose it connects to the other factors a and b. So the message value from this x to f can be just the summation of the message from fa to x and fb to x. But when we do the argmax, we know when we compute the message from fa to x, we have a table. So let me just draw the table. So suppose it's x, and the other variables connecting to fa is x1, right? So this is x1, and fb connects to the other variables x2, right? So for the when we compute the message from fa to x, when we compute the argmax, I'm gonna have a table like x equals to 1, and the optimal setting of x1, which achieves the maximum, will be 2, and x takes to 2, x1 could be 3, until k, like x1 could be k minus 1, okay? It's table 1. Right? Similarly, I'm gonna have another table when we compute the message from fb to x, right? So this table records, okay, when x take each value, each possible value, what is the optimal setting of x2, that maximum corresponding summation in the message. Does it make sense? Right? So, see, 1, I just blindly drop down, right? 1, 2, like 3, blah, 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 right? So now, I have these two tables, these two argmax message, right? So now, if I compute the message from x to f, how can I compute? How can I do the argmax? Yes, I just merge the two tables. So now this table has 3 columns, right? So first column will be x, recording the possible values x can take. The second column will be x1, the third column will be x2, right? So when x is equals to 1, then I know the optimal setting for x1, which connects to fa, will be 2, and x2 will be 2. And then when 2, okay, look at this one, this row, and this row, drop down as 3 and 3, and continue. So now on this big table, right? This is how we compute the argmax message when we have a message from a variable factor. You just do it alternatively until you arrive at the root node and until you distribute the message back to the leaf nodes. Does it make sense? So now let us look at the detailed example. So I'm going to use the example you guys are familiar with to illustrate this procedure, such that it won't be confused at the homework. So suppose I have a factor graph like this. This is x1, this is x2. This is x3, this is x4, so this is f A, this is f B, this is f C, this is f D. So in a previous example, I don't have this factor at f D, but I want to add a little bit more complexity to give you the more general example, right? So we want to use maxsum to compute the maximum joint probability of this factor graph, and also to find out the configuration of x1, x2, x3, and x4 that achieves this maximum joint probability. How can we do that? So FC other than x4, right? So it will be x2. So this message from x2 to C, x2. Then you do the max. Max over x2. Right? So this one is straightforward. So let us look at it again, right? How can we compute the argmax, right? So the argmax will be just argmax, and this thing just move here, right? So now, with that being said, we have another table, right? So this table, let me simply draw it here. So you have x4 here and x2 here. So we have x4, see, when x4 is 1, the optimal setting of x2, which maximizes summation, will be like 1, right? 2 might be like k, blah, 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 until k might be like k minus 1. I just blunder right now. So now we capture the message from x4, from fc to x4. Right? So now you can follow this procedure, and then you distribute the message back from the root x4 to all the leaf nodes. I won't repeat this forever, right? So now let us look at the case step, right? Suppose I have done everything. I want to find out the maximum joint probability and all the setting of x1, x2, x3, x4 that arrive at this maximum. Right? How can we do that? How can we link those tables back to find out setting, right? So this is the most exciting part. So now we have all those kind of tables. So when we have all the messages ready, we just look at x4. Of course, you can look at x2. Doesn't matter. Doesn't matter at all. Right? I just look at x4, and then I add up all the incoming messages. So I have 2 incoming messages, right? So I have a new FC, the message from factor FC to X4, plus message from this leaf factor FD to X4, right? So to calculate the maximum drawing probability, or in other words, it should be calculate the maximum log drawing probability. So I'm gonna maximize this summation of incoming messages, right? And when I find a maximum value, I end up with a maximum log drawing probability. At the same time, I want to find out which particular setting of X4 that makes the summation largest, right? That will be corresponding to the optimal setting of X4 itself. Suppose I end up with the optimal setting, so it's still argmax operation of X4 will be, say, X4 star to be 2, right? Now how can I trace back to find out the setting of all the optimal setting of all the other random variables? We just look at this table, right? Those argmax messages, they are just tables, right? So okay, I say okay, X4 star is 2. I mean X4 star is 2. When X4 star is 2, I find out the maximum log drawing probability, and then I look back at this message. So that is when I calculate the message from FC to X4. What is the optimal setting of X2 for each value of X4, right? So when X4 taken to the, say, the 2, then I know the optimal setting of X2 will be K, right? So X2 star will be K. And now I look at when X2, the optimal setting of X2 is taken to be K, what is the value, what is the optimal setting of the associated variables value? And then we'll look at this table here. Right? This is computed when I compute the message from X2 to FC, right? It will associate with setting of X1 and X2. So okay, we found okay, X2 star, the optimal setting of X2, which arrives with maximum drawing probability, is here, right? Then we know the optimal setting of X1 star, X1, X3 star is here. Then we finish. What? How about what?
We still have.
Yeah, you still have a table here, but it doesn't matter. As long as you can cover all of the random variables, it's fine. As he mentioned, right? We actually do not need to merge the table. As long as we can find out, we can trace back which are incoming messages to compute the message from X2 to FC. You can trace back the 2 tables. You can look up the table as well. But here, I mean, for straightforward lookup, you can merge the table. If your tree is more complicated, you have like extension, many layers. You just link those tables again and again until you find out all the optimal setting of the random variables. Then you find the configuration of all the random variables which achieves the maximum drawing probability. Does it make sense? Is it more clear? I hope everybody at least captures the general sense. And then I will highly recommend you to do things like me, do this dirty work, and write down every step in calculate message and just imagine a table. You can blindly write down whatever values you want. And then you can imagine how you trace back to find out all the optimal settings. Doing that is more than sufficient to finish the homework. Remember, I have asked you guys to explain how do you find out maximum optimal configuration that maximizes the drawing probability. Okay. So now I think we can really we can finally finish the graphic model inference chapter. So next, I'm gonna briefly talk about our topic in the next big topic in the next section. So approximate inference. So I would like to first step back and look at the general picture, what we have discussed so far. Right? We spent quite a long time to review all the necessary foundations in probabilistic modeling. So what is the conjugate priors, what is unconformity priors, what is exponential family, what are their important properties. Without going through this, we cannot discuss about the advanced probabilistic models. And then we discussed the two types of the probabilistic models. First is the generalized linear models, right? Although we call generalized linear models, it does not necessarily only model linear relationships. Through the nonlinear basis functions, we can capture a variety of nonlinear relationships. And then we introduce a powerful modeling tool, a language, to build up probabilistic models. It's called probabilistic graphic models. This is a marriage of the graph theory and probability theory. So you can intuitively describe the relationship between your random variables and between your random variables in a graphical interface, right? And we introduced the general inference scheme on that. And later, in terms of the probabilistic models, we're going to introduce two types of very powerful, very hot models. The first one is called Bayesian neural nets. You can consider as the probabilistic version of the artificial neural nets, which is kind of double right now, but it's very hot. Right? So, and then we'll introduce another non-parametric model. It's called Gaussian process. As to why it's non-parametric Gaussian process, why it's called non-parametric model, I won't discuss about it. It's a big topic. But there is a surprising, striking connection between the Bayesian neural net and Gaussian process. So there's a famous theorem showing that if your neural network is infinite wide, it will converge to a Gaussian process. But before I introduce these two more advanced, more eyeball attracting techniques, we need to address some fundamental issues, right? We have like a bunch of powerful models, right? Expressive models very widely used. The issue is that how can we compute them? So giving you a bunch of data, right? How can you compute the posterior distribution? How can you do the estimation? How can you apply them in practical applications? Right? Without addressing these problems, when we talk about this, it's just like talking about something is in front of there, but you cannot use them. It's not meaningful. So we'll spend quite a few lectures in talking about the fundamental computational tricks to address the computational issues. So as we mentioned, rarely in practice, there are rarely models that can be estimated through like Bayes rule. We have to use all kinds of approximate techniques. So we'll mainly introduce three types of approximate inference techniques. The first one is called approximation. The second one is a huge topic, so variational inference. And variational inference actually dominates the estimation of the neural networks right now. And also Markov-Chain Monte Carlo sampling, which is considered as the gold standard because it preserves the asymptotic convergence to the posterior distribution. This is the only inference method which can guarantee you're going to converge to the true posterior distribution. And in practice, it usually performs better than the other methods. But there's no free lunch. MC is really hundreds times slower than those kind of methods. So people would rather sacrifice this accuracy. So, so in the next step, we're going to discuss these approximate inference schemes, and we'll give detailed examples about how to apply those schemes. And then with these powerful computational tools in hand, we'll discuss the nonlinear models we're going to discuss, right? So here's the whole lot. And the requirement for this section, I think I need to claim beforehand. First, we're going to go through many detailed mathematical derivations because the devils exist in details. If you want to master those techniques, you have to go through those mathematical derivations. So don't complain about that. But you still need to capture the key idea of those algorithms. If you can use one sentence to summarize what's the idea of each type of approximate inference techniques, that's wonderful. And then you are required to implement those approximate inference algorithms for a few well-known models. So this is, you have to operate on practical data, you have to debug your model, you have to prove that your implementation works. And in the remaining section, you will see many practical tests, as I mentioned yesterday. So you will see less and less analytical problems. You're going to implement more and more probabilistic models on real data. So this is just a brief summary of the tasks we're gonna do. So now let us look at the first type of the easiest approximate inference approach. It's called the Laplace approximation. So although it's very straightforward, but it turns out to be very effective. And so let's see what's the idea of the Laplace approximation. Oh, here's the outline. So we're gonna first introduce what is Laplace approximation, what's the general scheme for Laplace approximation. Then we'll use this Bayesian logistic regression as an example. So the key idea of Laplace approximation, that's my one sentence summarization. I just construct a Gaussian distribution to approximate target posterior distribution. That's it. So no matter what kind of posterior distribution is, I just construct a Gaussian distribution. Then the key idea is how can we construct such a Gaussian distribution, right? So the Taylor idea is that I use second order Taylor expansion at the map estimation. So basically I just run optimization and find out a mode of the posterior distribution. Then at a mode, I do the Taylor expansion. Use the second order Taylor expansion. I use this hash matrix to construct the Gaussian distribution. So specifically, let us look at the details, right? So suppose we are given a joint probability P of theta and D. So theta are the latent random variables. D are the observations, such as like in your regression you have like a bunch of continuous responses, right? Binary variables for binary observations. For classification problem, you have a 0, 1, 0, 1 labels, right? Also, you have like input feature vectors. Theta can be like weight parameters, whatever. And the key task in Bayesian inference is to compute this posterior distribution. What is the distribution of theta given the observed data, right? So Laplace approximation tries to approximate this posterior distribution in the following steps. So first, I'm gonna maximize the log drawing probability. I just do the map estimation. I find out the theta 0, which maximizes the log drawing probability. And then I extend the log drawing probability at the posterior mode, theta 0. So for convenience, let us just define this log drawing probability as a function of theta, because the observation D is just some kind of constant. So we only care about theta here, so we can define for brevity, we just define the log drawing probability as a function of theta. So now we can extend the function of theta at the posterior mode, theta 0. How can we do that? Just use Taylor expansion. So the first term will be the function value as theta 0, right? The second will be the gradient of the function as theta 0 in a product with the difference between theta and theta 0. The second term is half of this quadratic term. Theta minus theta 0 transpose the Hessian of your function at theta 0 and times theta minus theta 0. So this is a matrix. If you still have an impression of our 0 or 1, this This is a hash matrix, right? This is a matrix. But we will multiply a row vector on the left and multiply a column vector on the right. We'll end up with a scalar. Right? Don't confuse that. It's fine. And here we can only call it a Taylor approximation. Why? Because we expanded y at θ0. If you want this approximation to be equality, you cannot expand at θ0. You have to expand at some point between theta and θ0. Of course, this is just it's not very rigorous to write an integral on it. So basically, because there are two vectors, right? So theta here, θ0 here. So the exact equality will arrive at when you pick up some appropriate point in between theta and θ0. That's the definition of Taylor expansion, right? So if we directly expand it at θ0, I mean compute hashing here, this is just approximation. Right? And here we need to observe that because θ0 is a local maximum, right? Because the maximum drawn, because it maximizes the drawn probability. So it is it's a local maximum. With that being said, the gradient must be 0, right? That means the second term is simply 0. And interesting property is that the hashing at the hashing of the function f at θ0 will be negative semi-definite. Why? It has nothing to do with convex function. As long as this is a continuous function, it is twice differentiable, it is continuous, but the hashing is continuous, local maximum will always have a negative semi-definite hashing. So this is a basic theorem in optimization. If you open any optimization book, it will tell you why. I'm going to go through this, but I will first introduce the idea of the Laplace approximation. And then, based upon the time limit, I probably introduce the theorem, introduce the proof here or in the next lecture, right? So now let's assume like we acknowledge that okay, this hashing at the posterior mode is simply negative semi-definite. Right? So then we can define a matrix A, which is the negative hashing, which must be a positive semi-definite, right? I take minus in front of it, positive semi-definite. So now, and then we can rewrite this second order Taylor expansion by f theta 0. Remember, the first order term is simply 0, the gradient 0. And the second order term is minus half this quadratic term, right? A, remember, A is minus hashing, so I put a minus in front of it. So minus will be positive. So here, it's here. It's nice looking form. Remember our original definition, the f theta is logarithm of the joint probability. Okay. So then to recover the joint probability, I can take exponential on both sides, right? On the left-hand side, it becomes log joint probability. On the right-hand side, this is a log joint probability at theta 0, right? So if you take exponential of f theta 0, it becomes a maximum joint probability times exponential of this negative half quadratic term, right? So what does this look like? It's a Gaussian, right? This is a Gaussian. And now, if we use this term to approximate the joint probability, now I want to do the normalization. I want to compute the posterior distribution. What will be the posterior distribution? It's just Gaussian, right? It's just Gaussian. Because this one is constant, right? So as long as your distribution is proportional to this one when you do normalization, it just ends up with a Gaussian. Right? And in this Gaussian approximation, the mean will be still 0, which is the mode, posterior mode, comes from map estimation. Right? And the covariance will be the inverse of A. So remember, A is defined as a negative hashing of the log joint probability at the posterior mode. So you can see how we can construct the Laplace approximation. And I think the smartest point here is that, I mean, an elegant point here is that we know that since theta takes theta 0 in local maximum, this negative hashing of the log joint probability must be a positive semi-definite. With that being said, it is valid to be used to construct a Gaussian distribution. Right? So you can see that actually to obtain a Laplace approximation is a straightforward extension of map estimation. So when you do the map estimation, and then given that map estimation, you just compute the hash matrix. When you use hash matrix, you construct this posterior distribution. That's it. It's really, really straightforward. And in some cases, like people think, okay, if a theta is very high dimensional, right? So you have to compute this huge hash matrix. It's too large. So some approximation, I mean, even more aggressive approximation, I just compute the diagonal part of that. Then that means, okay, I use an independent posterior distribution to approximate the original distribution. Obviously, this is not very accurate. But in many cases, it's enough to use.
So if A is the positive subject, why are we using A inverse?
Because it comes from here. Because if you have a covariance, right, you have to do the covariance inverse here. So if you want to get to covariance, you have to take inverse of A. Any question? To give you a concrete example, so suppose this is our posterior distribution, which is proportional to a Gaussian term multiplying with a sigmoid function, right? So the yellow part here, this is a true posterior distribution. If you do the property normalization, whatever, you can compute this. We can see that it's not symmetric, right? But if you use Laplace approximation, you will not receive this red curve. They are aligned in the posterior mode, right? But other than that, it looks like this is not a very good approximation, at least visually. Right? But in practice, we are more interested in a variety of statistics computed from your posterior distributions. So it turns out that under normal conditions, like Laplace approximation can have many guarantees about your approximation error on different statistics. That means, in practice, it is enough to be used. Does it make sense? It's pretty straightforward, but it's very, very useful. And here, I will use the remaining 6 minutes to explain why this negative hashing should be semi-negative definite. Right? So if you're familiar with optimization theorem, you can just skip, or you can escape it right now. Right? Other than that, I would like to share with you some fundamental knowledge. So in general, I assume I just write down an arbitrary function fx. What I assume is that, okay, it is twice differentiable, meaning that I can compute the hashing in the domain, and also your hashing is continuous. So this is severely depends on continuity of the hashing matrix. Otherwise, it doesn't hold. It exists and also continuous. So suppose x0 is your local maximum. Meaning that in some neighboring, in some neighbor of x0, any value inside this neighborhood, say x, you have fx is less than or equal to fx0, right? So to show that the hashing at x0 is negative semi-definite, we can use a contradiction. Let's assume it's not negative semi-definite. Let's see what will happen, right? So if it is not negative semi-definite, that means at least there is this one vector such that non-zero vector p, such that this quadratic is positive. Here, semi-definite negative is positive, right? This is the definition of positive, semi-positive definite or semi-positive definite. If it is semi-positive, if it is negative semi-definite, means that for any such a vector, this quadratic term must be non-positive, right? If there is one particular case which violates that, it won't be called like negative semi-definite, right? So let us assume this is not negative semi-definite. That means there is at least one particular example is non-particular example such that P transpose hashing P is positive. Right? And remember, we assume that the hashing is continuous. That means at least there exists a positive value 50 such that for any small t, which is between 0 and t, you have this quadratic term where the hashing is evaluated at this t times p, still positive. Why? This comes from the calculus. Like if you have a continuous function, right? If you have a continuous function, like I know at some point, say x0, the function is positive, right? By the continuity, that means at least there exists one interval, non-zero interval. For all the inputs inside the interval, the function, the positivity of this function still holds. That's the continuity, right? It can be proved by whatever theorem, I forgot. But it's the basics. Right? So similar things happen here, right? Because this hashing is continuous. And the hashing, when the hashing evaluated at x0, this quadratic term is positive. That means at least there is a tiny interval such that for any point inside the interval, this quadratic term is still positive. This is very important. With this in hand, we can construct an input. This input, let me denote it as x tilde, which is x0 plus tp. And then, at the same time, I guarantee this x tilde is inside this neighborhood. It's very easy to pretend. I just look at whether this is inside. If it is not inside, just take t to be half and make the distance between x tilde and x0 to be smaller until it's inside this ball. It's just some technical details. So if I can construct a input x tilde, which is equal to x0 plus tp, I want to expand x tilde here. I want to expand x tilde exactly at x0. That means that, so the first term will be fx0, right? The second term will be the gradient of x0, x tilde minus x0, and the second term will be half x tilde minus x0 transpose. So here, remember, because we're doing the exact expansion, we're going to evaluate hashing not at x0. We're going to evaluate at some point between x0 and x2, right? So this point can be represented by x0 plus T prime P, right? So as long as T prime is between, and T prime must be between 0 and T itself, right? And then you multiply x to the minus x0, right? So here, this part is 0. Why? Because x0 is a local maximum, so the gradient is 0, right? You just throw it out. This part is 0. And we can take a look at this part. Remember, T prime is between 0 and T, right? That means T prime also between 0 and big T. Why? Because T is between 0 and big T, right? So from our previous conclusion, when any value between 0 and T, we have this quadratic term to be positive, right? So here, x prime minus x0 is just T prime P. So here is T prime P. Right? T prime is T prime squared. It must be positive, right? So the remaining will be P transpose and this Hessian and P, which will be positive. Does it make sense? So now we can say fx theta, it is exactly fx0 plus some positive term. It means that fx theta is bigger than fx0. So it contradicts with the fact that x0 is local maximum. Okay? So it's not possible. In that being said, your Hessian at x0 must be negative something. It gives the proof. Okay, so we have got the key idea of Laplace approximation. So see you on Monday. We're going to go through a detailed example of Laplace approximation.